All right, now is when we get into the most physicsy physics that we've physicsed so far this year. What do I mean by that? I mean, algebraically speaking, this is going to be the most complex part. So I want to warn you. I want to get you in the mood for it, okay? Now, I'm going to start by saying that this is all stuff that you've done before. This is all just algebra. It's basically just, systems of equations, 2 equations, 2 unknowns, 3 equations, 3 unknowns, right? And the goal here is to be able to analyze basic circuits. And by analyze, it means what are the currents that are going to be going through different sections of these circuits? All right, that's the big question. So on this slide, I skipped a couple slides that you'll have to refer back to in a second. But on this slide, it says, find the current moving through each resistor. Okay, how do we do that? How do we even begin to analyze, just knowing this, what will be the currents through these branches of the circuit? And we use a tool called Kirchhoff's laws. Okay, and there's only 2 of them, and they're very simple. Okay, the first of Kirchhoff's laws says that the sum of all the currents entering and leaving a junction must equal 0. Okay, so the sum of all the currents entering or leaving a junction must be 0. Again, let's look at where the junctions are, here and here. Okay, so this is the sum of the currents specifically at a junction must be 0. So if there's one I1 entering, then that must equal the I2 and the I3 leaving. Common sense, right? If I have a certain number of gallons per second flowing of water into this point, I need the same number of gallons per second flowing out. Otherwise, suddenly I have extra water or I've lost water to another dimension, which doesn't make any sense, right? So this is just saying conservation of charge, right? The current flowing into a junction must equal the current flowing out. Otherwise, we either have extra stuff from nowhere or we have less stuff than we should out of nowhere. Either way, it's too spooky for it to be real. Okay, second of the rules says that the sum of the voltage additions and drops around any loop must also be 0. So this is at a junction and this is around a loop. So in other words, that means that the voltage here that I add, this 10 volts here, minus the voltage drop that I lose at this resistor must equal 0 when I come back, right? And I know that might sound vague right now, but we're going to talk exactly about what that means. Okay. Through these 2 rules, we can solve everything we need to know about the circuit. And let me show you how. All right. So here we start. The first thing you do when you're analyzing one of these circuits, all right, is you're picking the direction of the currents. And this is totally arbitrary. Okay, you could be totally wrong. And if you're wrong, the current that you solve for in the end will just be a negative sign, in which case you know you need to flip the direction. Okay, so you can't be wrong about you can pick the direction wrong, but the result doesn't mess up your answer. It just tells you that if you get a negative answer, you just pick the wrong direction and you just like reverse it. Okay, again, I'll show you what that means. So we're going to pick the direction of the current around these various segments, and so remember, the current changes every time that you hit a junction, right? So through this segment, we will call this I1. Okay? Arbitrarily, I'm just naming that I1. Okay? So this is the first step. The first step is to pick the direction of your currents. And again, I don't know for sure that it's going in that direction, but I'm picking that direction. And if at the end I get a negative answer for I, it just means I picked the wrong direction. That's all. That's all. Okay? And then I'm going to say, okay, I then splits off here into an I2. Well, what did I pick? Actually, I called this I3 in my notes, and I called this I2 over here. Okay, so I'm picking I1 through here, and I'm saying I1 splits off into I3 and I2 over here. Okay, and so this direction would be this. And again, I could totally be wrong about these directions, but I'll find out at the end if I get a minus sign. Okay. All right, so that's our first step. We've picked our currents. Okay. Now, the next step is, well, from this we can basically say the sum of these i's equals 0, right? So here's the thing: we have I1 approaching this junction, and that must equal I3 plus I2. Okay, so I have I1 here, and then I2 and I3 are coming out of it. So I can create this equation. This is our very first equation of Kirchhoff's laws. We know that if we pick these right, I1 should equal I3 plus I2, right? If you want to phrase it in terms of this, another way to phrase it would just be I1 minus I3 minus I2 equals 0, right? It's the same thing, but I like this a little bit better. Okay. All right. So now we have to do our loop laws. Okay. So the whole goal of this, right? Right now we have 3 unknowns. We know that there's got to be 3 different i's in this, right? But we don't know what any of them are, so we need probably 3 equations to solve for 3 unknowns, right? That's the rules of systems of equations, right? So now we want to find new equations from the loop law, from the voltage law, okay? How do we do that? Well, we want to count all the voltage additions and drops around any given loop, okay? And now would be a good time to go to the previous slide that tells you your sign conventions for when you're adding around any given loop, okay? So